Welcome back to yet another episode of Dave Does Math from Home. Today, I have a very exciting one for you. Today we talk about trig derivatives. This is exciting because we've spent the last couple sections talking about how to do derivatives of like combination functions. When you multiply two functions together, how do you take the derivative of that with the product rule? Or if you divide two functions, how do you take the derivative of that with the chain rule? Lots of interesting combinations to be had here, except if we don't know how to take the derivatives of lots of different kinds of functions, it's going to get pretty repetitive. So I'm excited today to introduce new kinds of functions to do derivatives of. Up till now, all we've really had is polynomials. Polynomials come from the power rule plus the addition and subtraction coefficients are safe idea. That gets us any polynomial. We have any power function we want, so we got like square roots and negative exponents as well. And we have the standard exponential function e to the x. Those are the only three things we can do derivatives of until now. We're doing derivatives of trig functions. Let's start with sine. F of x equals sine of x. I want to start this out by talking about its graph. Sine of x does one of these maneuvers. And it does it infinitely. Keeps going. So I'm going to take a moment to sort of examine what kind of slopes we're dealing with here. Here at the origin we have a pretty positive slope. It's going up. It's pretty quick. Here I have, it's still positive, but it's not very positive. Here my slope is 0. Then I have a slope of gentle negative, strong negative, gentle negative, 0, slight positive, and I'm back to a strong positive to end this thing out. So, if I want to sketch a graph of the derivative of this, let me make sure that I'm color coordinating this nice. F of x, the original function, is here in green. So I'm going to sketch a graph of these derivatives. I need to start out with big positive numbers. And then I'm going to move to numbers that are still positive but sort of less positive. And then at this point on the x-axis I hit 0. And then I'm going to go negative. I'm going to go very negative. Less negative. Back up to 0. Positive. And back up to the big positive number right here. If I connect all these dots, hopefully this shape is extremely familiar to you, especially since, because the sine wave is periodic and keeps going, this should also be periodic and keep going. What we have here is a cosine wave, which sort of makes sense if you think about it. When we take the derivative of a sine wave, we need something that's going to switch between positive and negative and hit 0 here and here infinitely many times. Polynomials can't do that, exponential functions can't do that, logarithms can't do that, rational functions can't do that. There's only one kind of function that's going to switch between positive and negative infinitely many times, and that's another trig function. So the derivative of sine is cosine. That's very handy. Let's talk about the derivative of cosine. I can probably squeeze it down to the same thing. I'll just use a different color. Derivative of cosine needs to be, going to start at 0, and it's immediately going to go negative. The slopes here are pointing down. It's going to get to its steepest negative here, then a more gentle negative, as it comes back to 0, and then it'll be positive, steep positive here, slight positive up here, and back to 0. These are the, in red here we have the slopes of the cosine wave. 0, negative, it's decreasing. 0, positive, it's increasing, back to 0. So we need a function. It's going to start at 0. This red marker is not going to do it for me. Okay, this is my only other red marker. Better save the day. We need a function that starts at 0 and goes negative, but then less negative here, back to 0, positive, it's most positive here, less positive, back to 0. This red line looks like a sine wave, but the sine wave starts positive. This is starting negative. This red thing here, I probably haven't talked about second derivatives yet. Time for a brief interlude. If f of x is sine of x, then the first derivative is cosine of x. If you take the derivative of a derivative, which is a thing that you can do, when you take a derivative you get a function, and you can take the derivative of functions, so you can take a derivative of the derivative. That's how you get a second derivative. That's written like this, f double prime of x. So the second derivative of this function is, it's not sine. Sine goes up and then down, but it has that same shape. It goes down and then up. So it's a sine wave that has been flipped upside down. That's just called a negative sine of x. From here, if we want to keep taking derivatives, this is where it gets super easy. Because we already know the derivative of sine of x. And this negative business in front, that's just a coefficient. So if we take another derivative, it should just be negative cosine x. And if we take another derivative, at this point, instead of putting additional little tallies on it, you can just, in parentheses, write a 4. It's still superscript. You just use a numeral instead of increasingly many dashes. The fourth derivative of this, again, we know the derivative of cosine is negative sine. This negative sign in front is just a coefficient. So it's going to be negative sign, which is positive sign. We've come all the way back around to a positive sign. So this is pretty much the entirety of trig derivatives. Sine goes to cosine, cosine goes to negative sine. Negative sign is just where you started with a coefficient, so if you keep taking derivatives, you can just keep doing that. That's trig derivatives. So the next question is, what are we going to do with them? And I'm glad you asked, because I'm going to tell you. Let me erase this beautiful work of art first. When I started this video, I had zero expectation that this was going to come out looking half as good as it did. Okay, so as I was talking about when I opened this video, one of the big reasons we're talking about trig derivatives is so that we can have some more interesting functions to use in our quotient and product rule stuff. So let's talk about that. If f of x is 1/2 x to the 6th times the sine of x. And I want a derivative of this thing. I can get it. This is a power function. I know the power rule. I can take the derivative of this piece. This is a trig function. I know the derivative of sine is just cosine. I'm all set. I can just use the product rule, get myself a nice answer. So, product rule is the first, 1/2 x to the 6th, times the derivative of the second, which is cosine x, plus the second, which is sine x, times the derivative of the first, which should be 3x to the 5th. That's all there is to it. Individually, we can take these derivatives. Together, we know the product rule. We got this under control. Let's do a quotient rule one. Let's do a really interesting quotient rule one. I'm going to erase this so I have lots of room for this interesting quotient rule. Okay, here we go. F of x is tangent of x. This is the interesting quotient rule. Because tangent of x is sine x over cosine x. Now if we want a derivative, we have to use the product rule, or the quotient rule. Quotient rule says that the derivative is going to be the derivative of the top times the bottom minus derivative of the bottom times the top, all divided by the bottom squared. We can do this to this function. The derivative of the top is cosine x. The original bottom is cosine x. It's going to turn into a cosine squared. That's nice. I'm going to subtract the derivative of the bottom. Derivative of cosine x is negative sine x times the original top, which is another sine x. All of this is divided by cosine of x squared. Remember when I talked about the quotient rule and I said never ever simplify? That was good advice, but I'm going to ignore it here. We're going to simplify this. Turns out this cleans up really nicely. This is cosine squared. This is plus sine squared. The bottom is cosine squared. This is my favorite trig identity of all time, and incidentally the only trig identity I keep memorized because it's the only one that's actually important and worth anything. Cosine squared plus sine squared is 1. The derivative of tangent is 1 over cosine squared. Or, if you are a calculus textbook and you insist on perpetuating archaic, useless nonsense that should have died a couple hundred years ago, spoilers, that's every calc book in the world, by the way, unfortunately, you can choose to write this as secant squared x. I prefer this because secants are stupid and useless. The calc book is going to tell you this. Nothing I can really do about that until I write my own calculus textbook and then push all the other ones out of the market for trying to perpetuate stupid, useless nonsense hundreds of years after it's lost all relevance. So yeah, that's the derivative of tangent. sine over cosine, use the quotient rule, do some simplification. It's 1 over cosine squared. That's trig derivatives. I hope you enjoyed.